Hi, the topic we are going to discuss today is calculation of buoyant force. Let's begin. What exactly is buoyant force? According to Archimedes' principle, when an object is fully or partially immersed in a fluid, it experiences an upthrust, an upward force from the fluid surrounding it. That upthrust is what we call as buoyant force, and according to Archimedes' principle, the magnitude of buoyant force is equal to the weight of the fluid displaced by the fully or partially immersed object. Okay, now for basic understanding of buoyant force, this is a good enough statement. But if you actually want to do calculations, if you actually want to find out how much buoyant force acts on an object in a given situation, there is a better way to look at it. It is better to think of buoyant force as the force exerted on an object by the fluid surrounding it. Okay, let me write it down. What advantage does this way of looking at buoyant force give you? Let us understand this with an example. Consider a container which is filled with fluid up to a certain height. We are only considering a static fluid. Now, what is a static fluid? A static fluid is one which is in equilibrium with respect to the container in which it is present. Now, the container may be moving, may be at rest, but the fluid inside the container should be at rest relative to the container. Such fluids are what you call static fluids. So, let's consider a static fluid. Let's consider liquid itself present in a container like this. For now, we are considering a container which is at rest. Therefore, the liquid inside the container is also at rest. Okay, it is in equilibrium. This term is important. Equilibrium means the net force acting on the system is zero. Okay, so if you are saying the liquid is in equilibrium, it means net force acting on any part of the liquid is zero. Okay, let us consider one part of this liquid. You can take it in any random shape. I'm considering it like this. Now, since the fluid is static, okay, this part of the liquid that we have highlighted is in equilibrium. That means the net force acting on it must be zero. Now, what are the forces that act on it? One force that acts on it is its own weight. Assume this part of the liquid that we have highlighted occupies a volume V. And let's say the liquid that we have considered has a density rho. And if volume is V and density is rho, the mass of liquid in this boundary, inside this boundary, will be rho V. Therefore, the weight of the liquid inside the boundary, or the weight of the liquid we have highlighted, will be rho Vg, that is mg. Now, weight of a system can be shown as acting through its center of gravity. Now, for this highlighted part of the liquid, let's assume the center of gravity is here. So we can indicate its weight mg, that is rho vg, to be acting downwards through that point. Okay. What other forces act on that part of the liquid? Let's see. The liquid is surrounded by some more liquid, okay, and the surrounding liquid will be exerting a force at every point on the boundary of this highlighted part. Now, how do you express or how do you denote force exerted by a fluid? Now, we are considering ideal fluids. An ideal fluid exerts force perpendicular to the surface of contact, and that force arises due to pressure of the fluid. Now, we know that if the container is at rest, okay, pressure increases as we go down in the liquid. Okay. So on the upper side, the pressure is low. Therefore, the force exerted on this selected region on the upper side will be shown using a small vector. Okay. But as you go down, the pressure in the liquid increases. So you will need to indicate the force exerted by the surrounding liquid with slightly longer vectors. And on the lower surface, the force exerted by the surrounding liquid at each point will be even stronger because as you go down, the pressure increases. Okay. Now, these small vectors that we have drawn around the selected part of the liquid indicate the forces exerted by the surrounding liquid on that part. Okay. And the resultant of these vectors is what we call as buoyant force. Okay, that is what I was saying a little while ago. Buoyant force is the force exerted on an object by the fluid surrounding it. Okay, now we have not assumed any object to be immersed inside this liquid yet. Okay, we are just considering a part of the liquid itself. Why are we doing that? Because we want to derive an expression for buoyant force in the proper manner. Okay, we are looking at how it was found that buoyant force is equal to the weight of the fluid displaced. Okay, so we'll assume the fluid itself is present, not something else. Why? Because if the fluid itself is present, it will be in equilibrium. Okay, you won't see this part of the fluid sinking and some other part of the fluid rising up. Okay, the entire fluid is at the same temperature, there won't be any sinking or rising happening. So this part will be in equilibrium. If you immerse something else in the fluid, like a stone in water, okay, you know that a stone will sink in water, okay, or if you immerse a football in water, you know it floats, right? So those are objects which will not be in equilibrium, so you can't use them to derive an expression for buoyant force, okay, but the derivation is what we are doing. So we'll assume the fluid itself is present inside that boundary that we have considered. Now we know that this part of the liquid that we have highlighted is in equilibrium. Equilibrium means the net force on that part is zero. Now one obvious force acting on it is its own weight, okay, rho Vg. So we can say that the weight of that part of the liquid is being balanced by the resultant of these vectors that we have drawn around it. So basically the weight of that part of the liquid is being balanced by the buoyant force acting on it. Okay. Now, what is the weight of the liquid in this region? Rho Vg. Then that itself should be the magnitude of buoyant force acting on that part of the liquid, the part that we have highlighted. Okay. It means the resultant of all these small vectors that we have shown, all these small forces that we have shown acting on the surface of that part of the liquid from the surrounding liquid. Okay. That resultant is equal to weight of the liquid inside that volume, inside that space that we have considered. Okay. Now, in this space, if some other object is introduced, right? Uh, if some other object is introduced now, which has the same volume as the liquid that was present in that space. See, the space occupied is same, means the volume is same anyway. Okay. But let's say this object's density is different from that of the liquid. Let's say it has a density rho naught. Okay. And let's call the liquid density as rho L. Fine. Now, the weight of this object will be different from the weight of the liquid that was present in that region. What will the weight of this object be? Its density is rho naught, but it's occupying the same volume V. Therefore, its weight will be rho naught Vg. Let it be. What we are more interested in is the calculation of buoyant force acting on it. Okay. Now, buoyant force is the force exerted by the surrounding fluid. Now, whether this space is filled by liquid itself or some other object, the surrounding fluid situation is the same. Okay. That means the pressure distribution in the fluid surrounding this object is the same as what it was before. Now, if the pressure distribution is same, the forces that the surrounding fluid exerts, okay, those small vectors that we have considered, they will be the same because how do you calculate force exerted due to pressure? Force, small amount of force dF can be taken as pressure at that point multiplied with the area dA. Okay, so if you consider a small area here, the force acting on it due to pressure will be PdA. Now, whether this space is filled with the object or the liquid itself, surrounding fluid is the same. So pressure distribution in the surrounding fluid will be the same. Therefore, the forces acting will be same. Now, the resultant of all these small vectors, which is what we called as buoyant force, earlier it was in the upward direction. How do we say it was in the upward direction? It was balancing the weight of the liquid present there. Okay. Weight of the liquid was acting downwards, so buoyant force must have been acting upwards. Now, since the vectors are the same, the force will still be the same. Therefore, the buoyant force acting even now will be same as what was acting earlier. Now, how much buoyant force was acting earlier? Density of liquid into volume immersed into G. Okay, rho L Vg. That was the buoyant force acting. The same buoyant force will act even now, but the weight of the object has changed. Okay, so now look at the forces acting on this object. One force acting upward, if you draw its free body diagram, one force acting upward is the buoyant force, which is rho L Vg. Another force acting downward is its own weight, which is rho naught Vg. Okay. Now you know how much buoyant force is acting and how much weight is acting. Based on which density is greater, okay, whether the liquid's density is greater or the object's density is greater, you can tell what is going to happen to the object, whether it is going to rise up in the fluid or sink in the fluid. And if densities are equal, the object will stay where you released it, because the net force is zero. Why will it accelerate? Why will it move up or down? Okay, so this is the basic reasoning or derivation of buoyant force, and why buoyant force is equal to weight of the fluid displaced by the object. But this is not always the case. Let us consider a different situation now. Consider a container filled with a liquid. Assume the density of the liquid is again rho L. This time, imagine the container is accelerated upward. Let's say its upward acceleration is A. It is possible that the container is present inside an elevator, or by some means it is being accelerated upward. But the fluid is static. What does that mean? As I explained earlier, the fluid being static means the net force on any element of fluid inside the container is zero with respect to container. Not with respect to ground or someone else. With respect to container, it must be zero. Okay. Now let us consider a random part of this liquid that is present inside the container. What are the forces that act on it? One force which will definitely act on it is its weight, which will be expressed in terms of its volume. Let's assume the volume is again V. Then the weight of that part of the liquid, it acts through the center of gravity. It will be rho L Vg, density of liquid into volume of that part of the liquid multiplied with acceleration due to gravity. What other forces act on it? There is force exerted by the surrounding fluid, which we indicate by showing small vectors, okay, at different points on the surface. Since the container is accelerated upward, we know that the pressure increases as we go down, okay, in the liquid. Therefore, the forces from the surrounding liquid on the lower side will be stronger than forces from the surrounding liquid on the upper side of this object, not object, on this part of the liquid that we have considered. Right. Now, the resultant of these forces is what we call as buoyant force, and the expression for buoyant force in this case is what we are trying to derive. Okay. Let us consider what other forces also act on this. Now, this part of the liquid, in fact, any part of this liquid must be in equilibrium relative to the container. The container, as you can see, is accelerated. Therefore, it becomes a non-inertial reference frame. Fine. And whenever you are analyzing a system from a non-inertial reference frame, you are supposed to consider a pseudo force. Fine. What is the expression for pseudo force or formula for pseudo force? Mass of the object on which you are applying it. The object on which we are now going to apply pseudo force is this part of the liquid. Okay. So we have to take mass of that part of the liquid, which is rho L into V, and you have to multiply that with acceleration of the non-inertial frame of reference. Acceleration of the non-inertial frame of reference, which is the container, is A in the upward direction. So pseudo force will be rho L V A. And what is the direction in which you apply pseudo force? Opposite to the direction in which the non-inertial frame is accelerated. The container is accelerated upward, so you'll need to consider a pseudo force in the downward direction. Let us indicate that. And pseudo force, the point of application of pseudo force of an object is its center of mass. And for small objects like this small volume that we have considered, center of mass and center of gravity will coincide. So you can imagine pseudo force acting like this. Mass of the part of the fluid rho LV multiplied with acceleration of the non-inertial frame of reference. Right. So one force acting on it was its weight. One force is the pseudo force because we are observing it from a non-inertial frame of reference. And the other force acting on it is the buoyant force. And under the influence of these three forces, this part of the liquid is in equilibrium. Equilibrium is net force being zero. Now its weight and pseudo force are both in the downward direction. Therefore, the buoyant force in this case must be in the upward direction, such that the net force on this part of the liquid becomes zero. Fine. And because it is in equilibrium, the upward force acting on it must be balanced by the downward forces acting on it. Therefore, we can now say that the buoyant force in this case is rho LVG plus rho LVA. Therefore, the buoyant force now becomes the sum of these two, that is rho LV multiplied with G plus A. The part of the liquid that we have highlighted experiences this much force in the upward direction in this case when the container is accelerated upward. So how are we calculating this? Remember that we are looking at the forces exerted by the surrounding fluid, and that arises due to pressure variation, okay, or pressure of the surrounding fluid. And we are ensuring that the part of the liquid that we have considered is in equilibrium relative to the container. We are just writing the equilibrium condition and deriving the buoyant force acting on it. Now, if that part of the liquid is occupied by some other material, okay, let's see what happens. If that part of the liquid is occupied by some other material, the only thing that changes is the weight of that material and the pseudo force that acts on it. Buoyant force, which is force exerted by the surrounding fluid, depends on the pressure distribution in the fluid surrounding it. Now that is the same because pressure in the surrounding fluid depends on depth of that point inside the fluid from the free surface and the acceleration of the container, of course, and the acceleration due to gravity as well. But it doesn't depend on what is present inside this space. Okay. So these forces that we have shown, the forces exerted by the surrounding fluid, will be the same whether this space is filled with this material or the liquid itself. Okay. Therefore, the buoyant force acting, even in this case, will be the same as what it was earlier. And how much was it earlier? Density of liquid multiplied with the volume immersed multiplied with G plus A. The buoyant force even now will be the same. Let's consider another situation where the container is accelerated horizontally, and in that case we will find out how much is the buoyant force exerted by the fluid surrounding it. Consider a container which is accelerated horizontally to the right as shown here. Now we know that when a container is accelerated horizontally, the free surface of the liquid inside the container is not going to be horizontal, it will be tilted at an angle, and you also must have done the calculation that the angle with the horizontal will be tan inverse A by G. Okay. So basically in this case, there is pressure variation as you go down in the fluid, and there is also pressure variation when you move sideways at the same horizontal level. Okay. Our aim now is to derive an expression for buoyant force in this situation. The procedure is going to be the same. Okay, we will consider some part of the liquid. We'll ensure it is in equilibrium. For that, how much ever force the surrounding fluid has to exert, that is the buoyant force. So consider some part of this fluid, some part of this liquid. Now, the liquid is static relative to the container, means this part of the liquid experiences zero net force relative to the container. What are the forces acting on this part of the liquid? One obvious force that acts is its weight, that is density of liquid multiplied with volume of that part of the liquid multiplied with acceleration due to gravity. Another obvious force it experiences is the force from the surrounding fluid. Okay. Now, force from the surrounding fluid depends on the pressure in the fluid. When the container is accelerated horizontally, we know that the pressure gradient is at an angle like this. Okay, the what do we call it? The maximum pressure gradient is at an angle like this, perpendicular to the free surface. Okay. So the force acting here will be a weak force, and as you go away from the free surface in a direction perpendicular to it, the forces become stronger and stronger because the pressure increases. So you can indicate the forces like this. As you go away from the free surface, the forces must become or must be indicated stronger. Fine. So these are the forces exerted by the fluid surrounding this part of the, liquid surrounding this part that we have considered. What other forces act on it? We are observing this part of the liquid relative to the container. The container is accelerated, therefore it's a non-inertial frame of reference, and you will again have to apply a pseudo force. Now, how to apply pseudo force? Pseudo force is mass of the object on which you are applying it multiplied with the acceleration of the frame of the reference from which it is being observed, and in a direction opposite to the acceleration of the frame of reference. Therefore, the pseudo force now must be shown in this direction. Okay, must be applied in this direction. And how much will it be? Density of liquid multiplied with volume. That becomes the mass of the object on which you are applying it multiplied with the acceleration of the frame of reference. That much pseudo force acts on it. So weight, pseudo force, and the resultant of all these forces exerted by the surrounding fluid, and that is what we call as buoyant force. These are the three forces acting on this part of the liquid that we have considered. Now, the resultant of weight and buoyant force must be balanced by, sorry. Now, the resultant of weight and pseudo force must be balanced by the buoyant force. Okay, that's the only way in which this part of the liquid can be in equilibrium. Weight is vertically downward, pseudo force is acting to the left. If you use the parallelogram law of vector addition and draw their resultant, the resultant of weight and pseudo force is like this, is in this direction. And how much is it? Since the vectors are perpendicular to each other and rho LV is common, the resultant of weight and pseudo force becomes rho LV under root G square plus A square. This resultant must be balanced by the buoyant force acting on this part of the liquid. Therefore, the buoyant force must be acting this way. And in direction, it is exactly opposite to the resultant of weight and pseudo force. In magnitude, it is exactly equal to the magnitude of resultant of weight and pseudo force. Therefore, the buoyant force in this case, when the container is accelerated horizontally, can be expressed like this. Density of liquid or density of fluid that is displaced by the object multiplied with the volume immersed multiplied with under root G square plus A square. So if you look at buoyant force this way, you can calculate it properly in any situation. Okay. Here, we can clearly see that the buoyant force experienced by that part of the liquid, even if you put some other object in that space, it will experience the same amount of buoyant force. We can clearly see that the buoyant force experienced by this part of the liquid or an object is not equal to weight of the liquid or fluid displaced. The weight of the liquid or fluid displaced would have been rho L V G only. But look at the buoyant force acting in this case. It's not equal to weight of the fluid displaced. Okay. So Archimedes' principle, which states that the buoyant force or upthrust experienced by an object is equal to weight of the fluid displaced, is valid when the container is at rest or in equilibrium. When the container is accelerated, buoyant force changes. And this is how you can find out buoyant force in any case. So what are the things that you need to know? one thing you need to know is how pressure varies based on the acceleration of the container. So first thing you need to think of is pressure distribution in the fluid. This will help you visualize the forces exerted by the fluid surrounding the object, and it will also help you visualize the possible direction of resultant, the possible direction of buoyant force. Next thing you need to know is whether the container is accelerated or not. If it is accelerated, which way it is accelerated, because you need to apply pseudo force. So next thing you need to consider is pseudo force. And then obviously weight and any other forces that may act on it. Right? Now, on an ideal fluid, these will be the only forces. There won't be any additional forces acting. So if you consider these three and write the condition for equilibrium of that part of the liquid relative to the container, you can derive how much buoyant force acts in any case.